Hi, my name is Vaijayanti. Today I'm going to be explaining about my intelligent systems assignment. I've implemented A-star algorithm for path planning and Q-learning for reinforcement learning. And I've also developed a game board using Tkinter module in Python. Um, Let me go ahead and get started. So when I run my algorithm, my GUI is getting invoked. So I have two different features right here. So I can either create my own map or I can open an existing map which I've already created. So let me go ahead and create a new map for this time. So I can select my starting position, my goal position, and I can even add obstacles here. But for this time, I'm just going to keep it simple. Once I'm done with defining the parameters, I can just close this and my game board will open for me. So this is my game board right here, and the features are as follows, as you can see. So when I run an A-star algorithm and hit the explore path or pause button, it's going to work for the A-star algorithm. And similarly, when I run the Q-learning algorithm, this button is going to work for the Q-learning algorithm. And similarly, this widget is also used for the same. I can increase or decrease the speed as required. So let me now explore the path. You can see that the robot has expanded this, and this was the start position. This was the goal position. The robot just took this path to reach the goal position. Now let me just go ahead and show you a bigger map. This time I'm going to use a pre-existing map. This is a very big map. So let me explore the path. So I've used something called the tiebreaker scheme. So the tiebreaker scheme helps us to ignore the unwanted paths that might probably be explored, thereby reducing the number of expanded nodes. So this is the expansion without the tie-breaking scheme. I'm going to show you the same map with a tie-breaking scheme, for which I just have to uncomment a line in my code, and let me just run the same map. You can see that without the tiebreaker scheme, this cell and this cell was expanded, but with the tiebreaker scheme, we have reduced the number of expansion nodes. So this is all about A-star algorithm. Let me go ahead and explain Q-learning. Oh, I just forgot to mention. So when my A-star code runs, I have these values that are being printed out for me. So I have the size of the grid, and I have the grid map, which defines the different things that are on the grid. Say, for example, zeros talk about the unoccupied space. Unoccupied spaces. One denotes the obstacles, in our case the ghosts. 2 denotes the start position, in our case the start button. And 3 denotes the goal, in our case the goal button. And once this algorithm runs, we have an action expansion, we have heuristic values that are being generated, and we have the expanded grid, the cost associated with the grid, and the coordinates that are being explored. All these values are being printed over here. So that is all about A-star algorithm. Let me go ahead and run the Q-learning algorithm. First, let me show you the deterministic version of Q-learning, followed by the stochastic version of Q-learning. So I'm going to use pre-existing Q maps for this, and I'm planning to use a small Q map. So, so for the Q-learning, you can change these features. You can change the discount rate. You can change the start node. You can change the exploration, that is the epsilon value. So if you change the epsilon, if the epsilon is 0, it is going to take the optimal path, that is, it is going to be greedy. If you change the epsilon values, say for example, the higher the epsilon values become, the random the actions that it is going to take. But however, even if it takes random actions, I have 0.1 probability of this going into an optimal state or choosing the optimal path. So my Q-learning algorithm has implemented softmax policy. Let me just go ahead and run this for you. So this is the deterministic version of Q-learning. So you can see the different values that are being printed and the different episodes. In deterministic learning, what happens is that the transition model behaves in a way that the robot will never land in this area. So I have used a haunted house over here, and I have associated a reward value of -1 to this. So if the robot learns that this gives a negative reward, it will never go here. And you know why this is exploring randomly? It's because we have kept the exploration epsilon value to be 0.9. Now if I reduce the epsilon value to 0.1, to 0, it is going to start taking the optimal path. Let's just wait for it to learn the model, and after a few training episodes, it's going to take the optimal path. Okay, now you can see, let me decrease the speed a little bit. So it has learned the optimal path. This is the optimal path. So I can change the start node. So right now it is at 5, 0. I can probably make it 4, 2. So it has started from here now. If I make it 2, 2, it will not consider that as a start node, because 2, 2 is a ghost, which is an obstacle. So it wouldn't take an obstacle as a starting point. So it will continue to explore from the previously defined position. So this is all about the deterministic version of Q-learning. Now let me just go ahead and show you the stochastic version of Q-learning. So I'm going to use the same map to show the stochastic version of Q-learning, so that you will be able to understand the difference between the two explored paths. Let me hit on this. So in stochastic learning, for the same map, the robot chooses a different path to reach the goal. So in if you remember, in the deterministic version, it took a path like this to the goal. But after a number of training episodes, we will now see the paths that it takes using the stochastic version of Q-learning. As you can see, it has learned the path now. So it is taking this path. As mentioned in the report, I have highlighted the two different paths for the deterministic version and the stochastic version. So that's it about Q-learning. Thank you for watching and thank you for your time.